Hello everyone and welcome to lecture 10 of module 2 of the course on ecological economics. So in this lecture we will focus on abiotic resources, something which we discussed in lecture 9 but not so much in detail. So abiotic resources, that is the non-living resources that forms the material and energetic foundation of our entire economy. So the first question is, what are abiotic resources, right? So let us begin by situating today's lecture within the broader framework we have been building. In lecture 9, we introduced some, powerful conceptual tools like thermodynamics, the distinction between stock flow and fund services resources, and the concepts of rivalness and excludability. So in today's lecture, that is lecture 10, we apply all of those ideas to 5 specific abiotic resources, that is non-living resources: fossil fuel, minerals, water, Ricardian land, and solar energy. And we will talk about each of these. Now, the question is, why these 5? Because together they underpin the entire material economy, and they are all finite, not in the same way, but each in its own, distinct way. In fact, the most important takeaway from today's lecture is this: that abiotic resources differ from each other far more than they resemble each other. So understanding those differences is the key to sound resource policy. Okay, so now let's move to the first, resource, that is fossil fuel, and we call this as the stock question. So let us therefore look at fossil fuels in depth, right? Okay, so yeah, so the basic facts, first let's put up the basic facts. In 1995, fossil hydrocarbons, that is crude oil, coal, and natural gas, supplied 85% of global energy. Crude oil alone accounted for 38%, coal 25%, natural gas 22%. These are not renewable. They represent a fixed geological stock that accumulated over hundreds of years of, hundreds of millions of years. And crucially, we can extract them virtually at any rate we choose. If you remember, we discussed about the rate, at what rate you want to extract them. And that flexibility is both their great advantage and also their great danger. Now, how much do we actually have? This is harder to answer than you might think, because estimates of recoverable reserves are very, very difficult, very, very slippery. So oil company estimates depends heavily on price expectations and also political incentives. So here is an example that in 1997, 6 OPEC member countries collectively revised their reserves upward by 287 billion barrels. That is 40% more than the total oil ever discovered by in the United States. And they did this without a single major new discovery. So the numbers were revised for economic and political reason, not for the geological ones. So how do we think about the real limit on fossil fuel availability? The most useful thermodynamic measure is the energy return on investment. This is the ratio of the energy we get out of the extraction to the energy we put in. So how much we are taking out and how much we are putting in. So in 1950s, the ratio of that, in 1950s, 1 barrel invested in US oil exploration yielded approximately 50 barrels discovered. So the energy return on investment of 50 to 1. So by 1999, that ratio had fallen just 5 to 1. Right? So it was 50 to 1, now 5 to 1. Some projections suggested that it would reach 1 to 1. So which means the ratio of energy we get out of extraction to energy we put in will become 1 to 1, meaning we spend as much energy extracting oil as we get from it. By around 2000, that is what is the prediction that is something going to happen. This matters because the net recoverable energy from any oil field is not simply the raw volume in the ground. It equals the initial anthropic stock minus the energy cost of extraction, minus the loss of solar capture caused by the waste products of burning that fuel, that the last term, the damage to ecosystem that would otherwise capture solar energy is the hardest to measure. So, like for example, CO2, burning of fossil fuel leading to CO2 emission, how much is it damaging the ecosystem is the most hardest to measure, and therefore most likely to be ignored, as well. So that is the fact about the fossil fuel, the stock question. Now, if you look at fossil fuel, the sink will fill before the source empties. In the sense, look at it now more from a sink perspective. So many people miss that when we talk about fossil fuel, there is a limit. The more immediate threat is not physical depletion of the source; it is the filling of the sink. So when, like I have been telling you, when we burn fossil fuel, the fuel does not disappear. It returns to the ecosystem as waste, as carbon dioxide, sulfur, nitrogen oxide, heat, even oil spills, and various other byproducts. These are not accidental side effects, right? They are thermodynamically unavoidable. If you want to produce petrol by burning fossil fuel, there is no way that you can avoid the side effects. And on the scale at which we currently use fossil fuel, they definitely pose a serious threat. Now, let us go through the main categories of waste. First, right, climate change. Carbon dioxide and other greenhouse gases trap heat in the atmosphere. So at current emission levels, natural carbon sinks, that is, we also have natural carbon sinks such as forest, soil, ocean, they cannot absorb fast enough. So the first problem that you see is that the rate at which we are emitting CO2 is so high that it is not possible for the fund resources to absorb. It's beyond their absorptive capacity. Now, second is acid rain. Burning fossil fuels releases sulfur and nitrogen oxide, which acidify rainfall and damage freshwater ecosystems and forests. Third, ocean and air pollution, oil spills, and combustion by products damage both marine and terrestrial ecosystems. So, all of those living beneath the sea, beneath the ocean are also under threat. But there is a fourth, more subtle category that Daly and Farley emphasizes: the loss of solar capture. The waste products of fossil fuel combustion damage the very ecosystem, that is the forest, ocean, soil, that captures sunlight and convert it into biomass. This indirect cost, that is like several degrees of magnitude more difficult to measure than the direct pollution, and therefore far more likely that most of these, particularly the capacity of converting the captured sunlight into biomass, how much is getting degraded, is very difficult to bring under economic calculation. So the policy implication is stark. Of course, fossil fuels are what? Rival. Once used, that energy is gone forever. And stock flow, meaning we control how fast we open the tap, right? There is the rate at which we want to use it, we can control. We have been opening it, of course, wider every decade, but as we do so, we simultaneously are filling the sink. Meaning, more you use fossil fuel, it is not just that you are degrading the source, but you are also filling up the sink in a way that it is irreversible. And before the source actually empties up, you may actually degrade the sink to the capacity for the atmosphere, for the natural resources to absorb. It will go beyond their capacity to absorb. So that is why it is not just an issue of source, that you reduce the use of resource. It is also, when you use them more, you are also depleting the sink. So source and sink both are under threat. Now, moving on to the mineral resources. These differ from fossil fuel in one critical way: they can be recycled. But entropy still takes its toll, and understand how requires us to think, therefore, very, very carefully. How do you recycle them? So, like fossil fuel, mineral deposits vary in concentration. Concentrated ores are, of course, low entropy material. They are ordered, structured, easy, and cheap to process. As economy depletes the richest and most concentrated deposits first, it must move to progressively lower grade ones. So when the good ones are over, you obviously go to the next one, then the next one. So you move to the more lower grade ores. So processing these lower grade materials already accounts for roughly 10% of global energy use. And that share is now rising, as the quality keeps on declining. So this is very important to remember that the one which are best and cheap to process, we have almost already exhausted them. So now we are moving to those which are not very cheap to process. They require a lot more energy. Now, the recyclability of mineral creates two distinct types of waste, and the distinction matters a lot. The first type is what we might call as garbo junk, discarded goods that are still in a relatively ordered state. And what is that? For example, a old car, a retired car sitting in a junkyard. For example, in principle, the steel is recyclable. In practice, it may not be recycled because the original, the virgin oil or ore happens to be cheaper. This is an economic failure, not a thermodynamic one. Okay, so garbo junk could be recovered if policy got the prices right. So remember, many of these old things can be recycled if you have the right policy to recycle them. The second type is a pure waste, that is entropic dissipation. This is matter, I mean, this is important because this is like it has been dispersed atom by atom through mechanical or chemical processes, meaning think of penny of work. I mean, it requires a lot of work because this kind of dissipation really cannot be reversed. It represents an irreversible loss of material order. So this is this second type, which is really in a very, very poor form, are very difficult to also recycle. So this distinction also leads to an important concept to stocks to track. So underground, there is a finite subterranean stock of mineral oil ores. As we extract them, and above ground stock builds up in the form of cars, buildings, machines, appliances. The gap between these two curves, what went into the ground and what is currently in use, is above ground. Now, measures the cumulative entropic dissemination. So what is inside the ground and what is above the ground? It basically tells you that how much will be entropic dissipation that will happen. And that only gap only grows over time. Okay, so remember, underground is something which is the finite stock of mineral oil, and as we extract them, we call it as above ground stock, which is all these cars, buildings, etc. So more and more, so the gap, how much is there and how much you are using it up above ground, this gap is called as it measures the cumulative entropic dissipation, how much of entropy is getting generated. And now what we see in the present time in that this gap between what is there and what we are constructing is actually growing. And finally, a note on the key theoretical debate is that, as Rogan argued, that mineral depletion is actually more serious than fossil fuel depletion, because while we can find energy substitute, nothing substitutes for matter. Okay, so this is something we need to keep in mind. Now let's move to water, the more complex abiotic resource. So, water is most complex of the 5 abiotic resources we examine today, because whether it is a stock flow or fund service, rival or non-rival, entirely depends on how it is being used. So, let us start with some basic facts that would set the stage. Of all the water on earth, less than 3% is fresh water. Of that fresh water, only about 0.31% is accessible groundwater. Lakes account for just 0.009% of Earth's total water, rivers and a mere very small percent. Okay, rivers very, very small, and the Amazon is so large that roughly half of its rainwater is self-generated through evapotranspiration from its own forest. So a striking illustration of how ecosystem and water cycles are actually deeply interconnected or interlinked. Okay, anyway, so now water as a stock flow resource. When we drink water, irrigate crop, use it in industry, or dispose of waste into it, we are treating water as a consumable stock, because that water is getting used used up, at least locally. Many aquifers around the world contain what hydrologists call, as fossil water, water deposited thousands of years ago with negligible natural recharge. Once we pump it out, it is effectively gone on any human time scale. So major rivers, the Colorado, the Rio Grande, the Amu Darya, and several rivers in northern China are now so heavily tapped that they regularly run dry before even reaching the sea. Dams adds another stock flow dimension, allowing water to be stockpiled rather than flowing freely. But water is also, so this is about stock flow part where it becomes rival. It has a rivalrous nature and it's not available for others. But then water is also a fun service resource when used for transportation, recreation, ecosystem sustenance as a part of hydrologic cycle, the evaporation and precipitation that replenishes rainfall. So water provides a service at a fixed continuous rate without being used up. Hydroelectricity is an interesting case here. A run of a river microhydro plant harnesses water as a fun service resource because it doesn't consume it, it doesn't make it unavailable, converting the ongoing flow into electricity. So a large reservoir dam, but by contrast, converts the energy into a stockpile, making it stock flow because you store a large amount of water, making it difficult for the downstream to get access to that water. So although it is fun service here, but the large dam makes it rivalrous. That is why there is always an upstream downstream conflict when you dam water with a large dam compared to a smaller run of the river micro hydro plant. So the key principle is this, that fun service uses of water are non-rival. By using the river for transportation does not prevent you from doing so, or does not prevent anybody else from using that water. Stock flow uses are rival. So if I drink this liter of water, you cannot. So intergenerationally, however, water is essentially non-rival because it cycles through hydrological system indefinitely. And unlike almost every other resource, human cannot meaningfully affect the total global stock of water. We can only affect its usability and distribution. We cannot reduce or increase the quantity of water that is available. But what we can do is we can degrade it. We can reduce, make the quality bad. We can, keep it with us for some time. But overall, unlike other resources like fossil fuel, you cannot actually reduce the total global stock of water. And that is why we say that water has many characteristics. And so it is much more complex abiotic resource compared to other, because it has both, rival characteristics as well as non-rival, meaning stock flow and fund service characteristic. And overall, you cannot really reduce or increase the stock of water, global stock of water. Now let's move to another interesting, resource, that is Ricardian land and solar energy. And you will understand why we call it as a Ricardian land. So, okay, so these are actually two abiotic resources, Ricardian land and solar energy, and they share an important property. They are both fund service resources, and both are essentially indestructible, meaning you cannot destruct them. Okay, but each has its own unique policy implication. So let us start with the Ricardian land. So the term Ricardian land comes from the economist David Ricardo. You know David Ricardo, we discussed about it. Again, if you have forgotten, you need to go back to module 1. So Ricardian land refers to land as a physical substrate and location, right? As distinct from fertility of its soil, where we, group, with minerals. So just remember that it's a physical element and it has a location. It is in one particular place. Ricardian land, so not like water which flows, right? So Ricardian land is a fund service resource because a hectare of land capable of producing 1,000 tons of wheat over 100 years cannot be made to produce all of it in 1 year. You cannot do that, right? There is a capacity. Its productive capacity comes at a fixed rate. And nor can that capacity be stockpiled. You cannot save up a year's worth of land services and use them later, right? So therefore, we say that Ricardian land is a fund service resource because whatever a particular hectare of land is capable of producing, 1,000 tons of wheat over 100 years, it will produce it in that way, but you cannot stockpile it. Okay, so Ricardian land is ripe, but while it is fund resource, but it also, you have to remember, the Ricardian land is rival within a generation. If one farmer uses a field of crops, no one else can use that same field at the same time. But intergenerationality, it is non-rival and absolutely non-depletable. Using land does not wear it out in any permanent sense. So maybe if your land today, if you are using it at a very high rate, it become a fallow land. But maybe if you leave it out, it may retain its property and it may come back for the future generation. So for present generation, of course, it becomes rivalrous, because at the same time somebody else cannot use, but for intergenerational, it is still remains non-rival. One genuine exception is sea level rise from climate change, which can permanently inundate a low-lying land. Or for example, if a land gets eroded, or because there's flood, the land is completely taken away, then that land becomes basically rivalrous because the future generation did not have it. Ricardian land is also excludable. You can own it, fence it, and prevent it, and you can actually not allow others to use it. Again, remember, this is not the case for water. Now let's look at solar energy. The numbers here also are very staggering. The sun delivers approximately 19 trillion tons of oil equivalent per year to the Earth's surface, and that is most energy than all recoverable fossil fuel stocks combined. So imagine the power of solar energy, and which is and the sun will continue to shine for billions of years, long past any possible human extinctions here. I mean, it will, as of now, we know that it will keep shining. So almost all of this solar energy is captured by chlorophyll, by green plants, photosynthesis that we say, plants of the biosphere, which are themselves a biological fund service resource. So this is why it is very important that solar energy plays a very, very important role. Now, solar energy is non-rival and for practical purpose, non-excludable. You cannot really exclude somebody using the solar energy. No institution can own or allocate rainfall or sunshine. The alternatives to fossil fuel like biomass, hydroelectricity, wind power, photovoltaics, and also wave or ocean thermal energy, all ultimately is derived from solar fund. Here is the critical asymmetry to hold on to. Fossil fuels are stock limited but flow abundant. We can use them at any rate we choose until the stock runs out. Right? Remember this. So fossil fuel are what? Stock limited, but we can use it at any rate we choose to until they run out. Solar energy is stock abundant but flow limited. It means that the total supply over time is essentially infinite, but the rate of delivery is fixed. You cannot ask sun that, give us more energy today, stock it for tomorrow. We don't need it tomorrow, right? So while it is infinite in a way that it can be supplied over time, but the rate of delivery remains fixed. So that is why also it is a, fund resource. Now, it is also important that, with industrialization, humanity made the choice, often unconsciously, to depend on the stock limited resource rather than the flow limited one. So we depend more on fossil fuel compared to solar. Now we are talking about solar energy, but so far we always had depended so much on fossil fuel, but not so much on a resource which actually only had a limitation of rate of delivery, but otherwise it is kind of infinite. Total supply over time is essentially infinite. Okay, now let's look at this comparison table so that I can bring together the 5 resources in a systematic comparison. So fossil fuels, remember, are stock flow resources, non-recyclable, excludable, rival, both within and between generations. That is the most important thing to remember. Substitutes exist at the margin, but developing them takes time, and that time may be running out. So remember fossil fuels characteristic. Then comes the minerals. Minerals are also stock flow like fossil fuel, but they are partially recyclable, if you remember. They are excludable and rival within a generation. Between generations, they are only partially rival because some fraction can be recycled and passed on. If you remember, I explained to you there are two kinds. One can be actually recycled. For example, an old car, steel, etc., can be recycled. Like fossil fuel substitute exists at margin, but are ultimately non-substitutable at the fundamental level. Water is context dependent. Both the type of resource it is and its rivalness depends on the use. Groundwater stocks are rival between generations. If you extract too much groundwater today, it will not be available for the future generation. Water used as a fund surface is not. So, for example, if you are using it for transportation, for a small run-of-the-river project, and for most of its most important use, drinking, agriculture, water is simply non-substitutable. Ricardian land is a fund service resource that is indestructible. It is excludable and rival within a generation, but non-rival between generations. Future generations can use the same land without any diminishment. It is non-substitutable as a physical location because you cannot bring another piece of land if it is not there anymore or if it gets eroded. Solar energy is fund service, indestructible, non-rival, and for practical purpose, non-excludable. No one can own sunshine. It is also non-substitutable. Ultimately, all life and all production depends on this form of energy, that is solar energy. So this is something to remember, that all natural resources are produced by nature, not by human being. First important thing. So it is wrong to say that we are, in a way, we can control everything. No person or corporation created coal, made an aquifer, constructed a river, or built the sun. It's a very simple fact, but that's how it is. So this raises the deep question about who has a prior claim over these resources, right? Something that we need to actually explore in depth. Now, what these characteristics that we discuss means for policy, a very important point to remember. So the first dimension, let's take, is scale. So stock flow resources, fossil fuel, mineral, etc., can be depleted irreversibly. So as economy grows, it draws even larger flows from finite resources. When you are developing or a growing economy, you draw more. Eventually, the flow must decline. So that's about the stock flow. Fund service resources like solar energy, land, limits the economy size at any given moment, but do not limit total production over time, because your land is limited, but you can increase its fertility through various ways, right? Because they cannot be used up either. So whether substitutability allows us to escape scale limits is an empirical question. Its substitutes can be found and developed in time scale. Then limits are less rigid. So if you can develop certain technology, certain science, which can remove the issue of substitutability, then maybe your scale limits becomes less rigid. But developing genuinely new technologies takes time, and the future is uncertain. So we cannot rely on yet to be invented technology as a backstop. The second dimension is distribution. So the first question is about scale, right? So what we spoke about scale is that there is a scale, there is a limit to growth, because everything is not substitutable. But what we are saying is that, okay, suppose, let's say that science is so great that we can find substitute for everything, but till now we haven't. So we cannot go ahead without being sure that yet to be invented technology will help us getting out of the issue of scale. The second dimension is distribution. Like most abiotic resources are rival, as we discussed, right? When one person uses them, others cannot. Now, rivalries within a generation raises question of fairness in the present. Who gets to use these resources and in what terms? So if we use everything today, for example, fossil fuel, land, etc., then what would happen is that all the resources, we have today access to it will not be available for the generation to come. So while Ricardian land, by contrast, is non-rival between generation, but future people can use the same land without any. So if you remove all the fertility of the land, although the land is there, but it's a barren land, then you know that it is not legitimate for the future generation as well. The third dimension is allocation. Market can only function, as you know, for excludable goods. For non-excludable resources like solar energy and rainfall, market allocation is not merely imperfect is literally impossible. So you cannot buy and sell sunshine, for example. So, but in practice, market failures are very much there. So externalities means that prices do not really reflect the social cost. So these failures means that market allocation of abiotic resources almost always requires policy interventions to be economically and ethically desirable. So the allocation part is something to remember, that since everything cannot be brought to the market, if it is not brought to the market, we do not really know that what is, for example, forest, right? How much forest we should leave or how much forest we should use for our satisfaction. You cannot bring the forest to the market to identify a price, for example. So how do you then allocate these products which has an externality? So that is where the allocation issue comes in. So let me now close this lecture by putting together the big ideas from today's lecture. First, the EROI and the entropic limit, the energy return on investment. The EROI is energy return on investment, declines as the best deposits are extracted first. Eventually, extraction consumes more energy than it produces. This is not a market failure, it is a thermodynamic reality. So policy must appreciate it before it arrives. Second, above ground versus subterranean stock. So minerals exist in two places simultaneously, underground as ores and above ground in the artifacts and infrastructure that we build. The widening gap between what have been extracted and what remains in use and overground is a direct measure of cumulative entropic dissipation, matter that cannot be recovered. Third, rival versus within versus rival between generation. This is crucial distinction for intergenerational equity. Fossil fuels are rival both within and between generation. Using them now means future generation will have less. Minerals are rival within a generation, but partially non-rival between generation because recycling pass them forward. Ricardian land is non-rival between generation. The same land will be available for our grandchildren. Understanding which resource falls into which category determines which equity concerns are relevant. Fourth, garbojunk versus pure waste. Not all waste is the same. Garbojunk, discarded but still ordered materials, is potentially recoverable with right economic incentives. Pure waste, matter that has been the matter that has been dispersed cannot be recovered at any price. Policy must distinguish between these two categories. And fifth, substitutability and time. History shows that substitutes for specific resources have often been found at the margin, and this is genuinely encouraging. But time matters. If fossil fuel deplete or fill sink before viable alternatives are developed and scaled up, no backstop technology exists to step into the breach. So the window for transition is finite, and we do not know exactly how wide it is. So this lecture is very important in the sense that it is not just that you look at resources as a whole. Every resource, be it abiotic or biotic, has its own characteristics. But our policies looks at all of these resources as a homogeneous entity. But if you look at all of these 5 resources, as I discussed with you today, every resource actually has its own characteristics and requires specific policy if we want these resources to be sustained for now and also for the future. I'm going to stop here, and in the next lecture, we will turn to biotic resources and examine how living systems differs from the abiotic resources which we studied today. Thank you.